Hello, everyone. Welcome to the Endgame reactions. I'm willing to bet this moment Dr. Ko is probably going to, is currently doing, or probably already has sped run through some of these end reactions. They don't really fall into many categories, I would say. So there's sometimes kind of just new iterations on things that you've already learned. And the reduction agents that you see on screen are definitely an example of things you already learned. But for the most part, you're almost there. I believe in you. You've been doing good so far. And let's go ahead and let's talk about the worksheet. And then from there, we're basically going to be done. I'm so excited. So with that being said, let's talk about some more reducing agents. We'll begin with that. So LTBH, right? Mild reducing agent. Diol H is a strong reducing agent. If you're familiar with your reducing agents, just know that you probably know at this point that they will attack carbonyls and they'll reduce them, reducing the amount of bonds to oxygen. And so this is going to be no different, right? But we're going to go ahead and we're going to go through these questions one by one. All right. So first and foremost here, right, you probably are not too entirely familiar with 100% of what this does, but you should obviously know what SOCl2 is. That is chlorination. And so I do also encourage all of you to kind of pause the video and quickly kind of just do the question on your own if you can. Practice makes perfect. All right, cool. So chlorination happens. And then from there, right, LTBH, right, will get involved. You'll have a hydride, right? This isn't the full mechanism, by the way, but this basically should summarize very quickly kind of what happens here. So it's going to come into here. It's going to pop up onto here. We're going to go ahead and get a intermediate here. So we're going to get this. And then so that oxygen is going to be charged. You're going to get a Cl kind of chilling here on its own. You get the H, the hydride coming down here. Then from there, right, this lone pair is going to come down here. It's going to slam back down. The Cl is going to pop off, and you end up with your end product over here. It's going to be an aldehyde. An aldehyde, yeah, from H, LTBH. Alrighty. And moving on from here, right? Diol, very, very similar mechanism, very, very similar vibe, right? You are going to be reducing this ester over here. And so your H is going to be going matching the colors, don't mind me. It's gonna pop up onto here, right? And then you're gonna get this. Oops. Instead of color, it's actually legible. This pops off right here. Yep. And NaOH, H2O just helps take care of any of the proton transfers that need to be done. So yeah. End up with an aldehyde. Very, very similar. Yep. Okay, cool. And OR also, right? Any alcohols, right? O or ethanol, things of that nature, right? That's what the OR kind of here represents. It'll pop off, right? And generally, right, if it's big enough, it can be a stable even group on its own. Alrighty, now let's talk about one of the more challenging ones, right? Where you have a cyclic ester. And so cyclic esters, right? What we're going to be doing here is we're going to be breaking this ring apart, and you're going to be forming lactones. So with this being said, we're going to go ahead and do the full Diol mechanism. So let's redraw Diol up here. Diol. ALIBU, Indigo, Bravo uniform, from here, H here, right? And so this H is going to be chilling here for a little bit. And the first step is going to be that this oxygen over here is going to attack onto this aldehyde right here. End up something on this. Get plus charge on this bad boy right here. So you end up with an H right here. You end up with an I. All right. And then just make sure I count all the carbons from 1, 2, 3, 4, 5, 6, 7. Right. And here, this pops up onto here. All right, and then from here, the next step is that you're going to go ahead and make this intermediate right here. fairly certain all these intermediates have names, but we don't bother with those. That's fine. All right. Oh, this is a negative charge right here as well. So forgot about that. My bad. Then from here, you're going to go ahead. You're going to get a. Let's see what's going to happen here. Yeah. So with an aqueous workup, right? Assuming a lot of these reactions sometimes have assumed reagents, right? We're going to assume NaOH is being added into here. Right? Just assume that whenever you're doing these types of reactions, there's an OH potential here on its own. Right? It's going to attack that aluminum. It's going to cause a cascade of things to happen. It's going to pop down onto here. It's oxygen. Now, from here, the ring is finally going to break apart. So then the end result is that you're going to have some lines of this. Right, this is the oxygen that just broke apart. I'm going to put this right here. Oof. Still there right into space. I'm missing a carbon. Oh no. We gotta be very, very careful. Even I screw up carbon counts. Go ahead and make this H real quick. Alrighty, cool. And then from here, right, you're just gonna quickly do a quick proton transfer, right, to get rid of that negative charge on that oxygen, right? So I'm gonna put PT here. And so the answer is going to be something along the lines of this. One, two, three, four, five, six, seven. All right. However, be careful because sometimes, right, you could have people writing elements of this type of question like this instead. You could have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. This is just an equally valid drawing of this answer right here, right? Sometimes Dr. Koh could give you something along the lines of, please turn this into this as a synthesis, right? And you might be thinking to yourselves, what the heck spatially? That seems so crazy, right? But just remember, right, that with cyclic esters, right, you can basically, since these are alkanes in the middle, right, you can basically just twist them apart and make them in a more less sterically hindered conformation. So yeah, so just be careful of that. Beware that can happen. So over here, right, we have dibol, more dibol, and we're going to be reducing cyanide group, C triple bond N. And so this is going to be a very quick abbreviated mechanism, but it's basically the same as what you saw up there. You're going to end up with something along the lines of this, right? And since this is an abbreviated mechanism, right, we're just going to assume it's intermediates in the step right here. Right. This step right here is, as you saw up here, basically, essentially it would be the equivalent of probably this step right here. Yeah. And then, right, you have your little H there. Go ahead and drop this out. And then NaOH, H2O. Okay, so every single time you have a C double bonded to N, if you throw in NaOH to H2O, what's going to happen is that you're going to turn that C double bond N into a carbonyl. So you're going to end up with a aldehyde. A lot of these reactions just end up going to aldehydes. Love us some aldehydes and stuff. Okay, cool. So moving on, Friedel-Crafts acylation. Hopefully you guys have seen my video on that, right? I'm just going to highlight this right here. The end product, we're just doing predicted product or PTP. It's going to be this bad boy right here. right here. Okay. The other way that you can make ketones, right, is using organometallics. And then after that, just kind of washing it all down with HCl, H2O. And so, yep, I think it was very, in a similar way, right, to what we saw up here, right, with the N double bonded to C forming carbonyls. This is another option you can use. So we're going to go ahead and we're going to go and attack. So this is going to go onto here. I'm a big Li fan, so I'll use Li. And have some other lines of this. Oop, let's make that white. Right here. Forgive me, Max, if I sound a little under the weather. That's because I am. My family went to go see the Pasadena uh, New Year's Rose Parade, and we stayed a lot of time out in the street, and so it was very, very cold. My bad. All right, cool. And then once you get to the step, right, if you wash it down with HCl and H2O, you're going to end up with turning that into a carbonyl. Make sure I have enough. 1, 2, 3, 4, 5. No. All right, cool. All right, cool. So we're going to be attacking more of the carbonyls. Carbonyls will not be able to catch a break this entire video and this entire lesson. But essentially, hopefully you're catching on to the point that you can attack carbonyls like so. They're electrophiles, right? And you're going to end up with something along the lines of this. This is the general vibe of the different types of reactions we're going to be doing. Right. And you're going to end up with something along the lines of this. H. Okay, great. As a reminder, this was this. Yep. Okay, cool. So let's talk about the next couple set of reactions here. There's some words associated with the names of some of these reactions. They're not really the most important. I guess it probably would be really helpful for you to kind of figure out how this works. Oops, let me just attack through here. It's going to pop up onto here. And so from there, you're going to end up with a P, H, H here. And then, yeah, we're going to end up with this right here. This right here. And CH3. Okay. This is all going to be in red right here. This is all going to be in red right here. Yep. Okay, cool. And then from here, right, we're just going to assume proton transfers. So just use water, use a base, right? Assume aqueous conditions. And then from there, you're going to get rid of all the charges. And then once that happens, right, you are going to end up with this. This is your product. It's called a hemiacetal. Hemiacetal. Yep. A full acetal, right, would be if you had something on the lines of this. So full acetal be something like this. You have R, R, and you have OR on top, OR right there. But since we don't have esters on kind of both sides over here, so to speak, we don't have this, right? We have an OH here, so it's a hemiacetal, only half an acetal. Hopefully that makes sense. All right, cool. Next move over here, right? It's going to be, remember, every single time you have like a strong acid, just any type of decent acid, and you have a carbonyl, most likely someone's going to get protonated. And usually what happens is that if you protonate a carbonyl, you make the carbon underneath it, right? If you protonate this bad boy right here, you make the carbonyl underneath it, right? Very, very electrophilic. And then you can use that to help facilitate some chemistry to go on. Yep. So we're gonna put this. Then once this happens, right, your CN can come down. CN from here, right? I'm gonna go ahead and I'm gonna highlight this in a different color. CN from here, CN right from here, right? It's gonna tap onto here. This pops off right here. We're gonna have some lines of this. Yep. Then you're gonna end up with the CN chilling right here. Okay. This is considered a gem cyanohydrin. I can't. There's no space. Cyanohydrin. Lovely. Yep. Cool. Moving on from there, let's talk about more nonsense with carbonyls, right? So in acidic conditions, you can form hemiacetals, right? So let's say, for example, we had some lines of this, right? This is the same as the thing you saw earlier. You end up with a hemiacetal, right? Assuming that all the proton transfers have been taken care of. If you don't know how to do proton transfers right now or are confused as to where the hydrogens are going, I recommend you go back and you figure out how to do proton transfers ASAP. Yeah. And if you add another equivalent, right, of an R group, right, attached to an OH, you can end up with a full acetal. Right. With I'll highlight this in pink. This guy right here, right, is this guy right here. Yep. Okay. And with ketones over here, right, you can also form hemiketals. Right. They're like acetals, but they're with starting off with ketones right here. So yeah. So sorry, I mean it's hemiacetal. Acetal. Right. So this is a hemiketal. Similar mechanism to last time. Right. Oops, let me make this white. And eventually, right, you can do the same thing over here, right, where you can add another equivalent of an R group or whatever attached to an OH. And then from there, you can get the full ketol. Yep. Okay. Pink, pink. Yep. Alrighty, cool. So let's go over the actual mechanism for a hemiacetal, right, and eventually forming the full thing. All right, cool. So just to quick mechanism over here. Shouldn't be anything too crazy. I think the Jones mechanism is probably a lot more worse than this. But assuming that you have right acidic conditions, right? So you have HCl goes onto here, this pops off onto here, right? Quick proton transfer. You end up with something along the lines of this. And then from here, you have your R group popping up here. H. Oh, or honestly, low-key, I feel like this mechanism is just a one huge long stream of proton transfers. So yeah. And from here, proton transfer. Alrighty. And then from here, right? This is where one of the big rules of of organic chemistry that you've learned so far are kind of broken. So in this example, right, OH can technically be a good leaving group. I absolutely hate to break your bubble, but I mean, I'm sure you were taught at some point that you couldn't subtract like negative numbers, and then the next grade over when you learn math again, you were just like, oh, actually, you can subtract by negative numbers, right? And so that's just an example of an educational concept called lying to children, where you lie to people, you oversimplify things, people can understand them, then you go back and you break their dreams. Yeah, I've had my dreams broken a lot of times this quarter, I'm sure. I'm 12 minutes at the beginning of the quarter, so I don't know. I'm taking some organic chemistry, so who knows? Maybe I'll be scarred by the time it comes around. Yep, so this OH will be chilling on its own over here. Right, you get something called an oxocarbenium ion. Come down onto here. Oxocarbenium ion. All right. And then from here, right, this is actually considered a resonance structure. It's been a while, guys. It's been a while. And from here, you take your other equivalents. Take another R group. Come in, do an attack. And as a reminder, none of these reactions, right, are technically SN2. Yeah. Very, very long. They're not in all one step, and probably they're very kind of complicated. So I would consider them SN2. Right. And then from here, photon transfer, end up with your final product, which is going to be a full acetal. Just acetal, yeah. Yep. Okay, cool. Acetal. Some more little fun trivia with this. Acetal ketal formations are reversible, so it's a very high chance here you'll probably get something along the lines of this, right? Where if you add HCl, right, to an already full acetal, you can reverse that all the way back down to whatever the heck you started with. Which in this case, it's going to be this. And from there, right, you can reverse all the way back into the ketone that you started off with. Sorry, did I call this an acetal? My bad. This is a ketol. Back to ketol, yeah. Okay. More fun stuff. You can form cyclic acetals and ketols. So if you hated cyclic esters, I'm so sorry. Remember, I didn't make the class. Don't shoot the messenger, right? Okay, cool. So essentially, right, with this reaction, if you have something along the lines of this, right, if you have two OHs that are kind of on double OHs that are on the same little molecule together, and you have an acid, this is para toluene sulfonic acid, better known abbreviated as PSTOH, or no, sorry, PTSOH. PTSOH, right? You could form something along the lines of this. Yeah. Why would you need to do this? Well, you can usually use these to protect carbonyls, right, from being attacked. So the same way that you can protect OHs, you can protect carbonyls. Because as you know, yeah, we've been assaulting carbonyls this entire video. So yeah. And then from here, just if you add water and acid, you can just reverse it. So, good times. Whoop, whoop. Alrighty. So let's go on to amines. It's amines turn now. We're gonna stack some amines around. Amines around. Sorry, amines. Amines? Amines. I no, I means with an I. Amines. Yeah. Anyways. So we're gonna be doing stuff with nitrogens, right? So here we go. We're just going to attack onto here in a very similar way to how acetals and ketols form, right? Once this full reaction kind of goes all the way through, you're going to end up with a hemiaminol, right? So hemi means there's an OH attached to it, right? And there's going to be a amine attached to it. Then from here, right? Very, very similar. Sorry, we're using OH as a leaving group. I'm sorry to break your bubble, right? And you end up forming an imine. Ah, that's what they're called. I knew it. Imine. Imine. Cool. Almost sounds like I'm discovering things with you. And to be honest with you, I am. I am. Right. So this is going to be your hemiaminal. This is your imine. Yep. And then from there, just, proton transfer. Oops. Yep. Alrighty. So moving on from over here, right? This is an example, right, of you just kind of have to get used to what's being asked of you. So we established over here, right, that if you have an NH2 that's attached to an R group, right, eventually you're going to form an hemiaminal, but eventually your N group is that you're going to have an imine, right? And so based using this example over here, this explanatory example, I'm going to move this over here. Using this explanatory example over here, right, try to see if you can attempt this one on your own, yeah? Alrighty, so you should have gotten something along the lines of this. Yep. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, and you get H2O as a byproduct. Don't think that's really important, but yeah. All right, so this is your imine. Imine. All right, cool. So what happens if you have a secondary amine, right? As you can see here, right at the beginning, right, we had a primary amine, which means there's only one thing attached to it, right? Now, what happens if we have two things attached to it? R3. R3 is on both sides. Great. R groups on both sides. Well, you're going to form a bit of a different product, right? So we're going to do a really, really brief. I don't even know what we're doing here. I don't even know what to call it. It's probably just a hybridized abbreviated mechanism. You're going to end up with your hemiaminal, right? Hemiaminal is kind of like the pit stop to full aminal or whatever you want to do afterwards. Oops. Jumped the gun a little bit. Pops off over here in response. Then you're going to form an aminium ion. Oops. Sorry, I should probably follow the example over here. See over here. Alrighty. And then from here, right, your OH that you had pushed off originally, I'm gonna highlight this in yellow, right? OH can then come over here, takes a good nucleophile, sees an opportunity, right? Pops off onto here. And then something wonderful is going to happen, right? This is kind of like a semi-elimination here, right? Where, oh, wait, hold on. Sorry. Wrong thing I'm attacking here. I'm going to be attacking this H right here. There you go. There you go. That's the right mechanism. Then you're going to end up with this. This is called enamine. Right? It's the combination of an alkene plus amine. Okay, cool. So moving on over to the Wittig reaction. Last stretch here, right? So the Wittig reaction, all we're doing is that we're going to be making alkenes, right? So we've done a lot of reactions, right, where we go from alkenes to other things, right? But we're basically just going to be doing the kind of the opposite way around now, right? We're going to be making alkenes, and so yeah, this is a very very interesting reaction, I would say. I'd say it's pretty simple compared to some of the stuff that you've expected to do so far. So the first thing you're going to be doing here is you're going to attacking right here. It's going to do a quick attack right there. And then, right, we get PPH3 with a plus charge right here. Yep. You have an H here. I'll go ahead and I'll highlight this because it can get a little complicated. Highlight. Oops. Right. Popped off. Okay, cool. And then from here, you form your phosphodium salt. And you grab your base, OTBU from over here. Come in, grab an H, and this H is going to collapse onto here. Very awkward placement. Oh, sorry, not onto here. Onto, let me just make this a little more accurate. Collapses onto this atom in the center, carbon atom in the center. Okay. You end up with this. This. Well, phosphorus ylide. Oh gosh. Phosphorus ylide. Okay. This is like the first preparatory step. And then from there, if you grab this phosphorus ylide and you throw it into the ring with if you throw it into the ring with the carbonyl, right? Take this all the way up to here. It's going to do some pretty wacky stuff, I'd say. It's going to tack onto here. It's going to pop up right here. Then you end up with a PPH3 plus charge right here, right here, right here, right here, R3, R1, with negative charge that. And tack onto here. We'll tack onto here. And then, oh, oops, sorry. We already attacked that in the last step. This is going to already be a kind of attacked right here, right? And you're going to form basically something that looks very much like a box. It's going to be a box. Yeah. So it's going to be very, you're going to tack onto here. Then you're going to form a little box. I have a series R1. Alrighty, so let me just highlight this in different colors so you can kind of see what's going on here. Right, so this is kind of on its own. It's red. And then from here, the box is going to collapse. It's going to pop in here. This pops up onto here. And eventually, right, you end up with, there's some more space here. This R1, R2, oops, R1, R1, R2, R2. Gotcha. Yep. Okay, cool. So, that's all for this section, at least, right? I'm probably gonna pick up another video to talk about more reactions, but hopefully, right, you guys are able to kind of see some of the reactions that we have to do towards the end. I encourage you also to do these practice problems on your own, right? So I'm not going to spoil it for you here, but hopefully you guys are all studying well. And that was Chem 8B. Thank you all for coming along for the ride, and good hunting on your final. See you around.